Bismillahirrahmanirrahim. In this lecture, we are going to solve the Schrödinger wave equation in three-dimension systems. In this chapter, we will discuss the structure of Schrödinger equation for a particle in three-dimensional 3D potentials by using two different coordinate systems. First coordinate system is Cartesian and other is a spherical. In first topic, we solve the 3D problems in Cartesian coordinate. It means x, y, z coordinates. This is the one-dimensional Schrödinger wave equation. As you know, this is a kinetic energy part, this is potential energy, and this is the total energy. And this equation is known as time-independent Schrödinger wave equation in three-dimensional potential because here we involve x, y, z. This is a kinetic energy, this is a potential energy, but potential energy is three-dimensional, and psi wave function is also a three-dimensional x, y, z, and total energy in psi x, y, z. Del squared, as you know, is Laplacian, and h psi is equal to e psi. This is the well-known equation when the Hamiltonian operates on wave function gives total energy. Here, the potential can be separated into three variables. It means v x y z can be written as vx plus vy and plus vz. Uh, this means three-dimensional problem can be solved in one dimension independently. This is vx potential in x dimension, this is a potential in y dimension, and this is the potential along z axis. To solve this problem, we need to understand about the separation of variables. It means these are three variables. This wave function can be written as separately in terms of x, y, and z. And similarly, the total Hamiltonian, which is the can be sum of the energy or Hamiltonian along x-axis is Hamiltonian along y-axis or Hamiltonian along z-axis. It is the same Hamiltonian that we have done in fourth chapter of quantum mechanics. And the expression fhy are similar and vxy separated into three independent terms. Now the wave function. This is a wave function of a particle which is in three dimension. It can be converted into xx, yy, and zz by using the separation of variables. Just replace this wave function here in this equation. Substitute 1.3 to 1.2. Then we have these three equations, three parts of equation. This is a x-dimensional kinetic energy plus potential energy, y-dimensional kinetic energy plus potential energy, z-dimensional kinetic energy plus potential energy. And it's equal to the total energy. Here should be written as x, x, y, y, and z, z as well. And if we just take this term, actually here you take this term is equal to ex, and this term is equal to ey, and this term is equal to here x is here 1 over x. You can take here capital X, and This is the Schrödinger wave equation in x dimension. Similarly, the total energy of E x, E y, E z is equal to. It's very simple, just the kinetic energy and potential energy. And this is just like a wave function along x-axis. Now we are going to solve the free particle in three-dimensional. It means Vx, Vy, Vz is equal to 0. As you know, the concept of free particle is the potential energy is equal to 0, the total energy, the kinetic energy, then this particle is called the free particle. X dimension Schrödinger wave equation can be written in this way. Here, if you remember the fourth chapter, we write minus h bar square over 2m d2 psi over dx square dx psi. But rather than psi, we have here x. X is just representing the wave function, some wave function in x direction. You can solve this, and we have this is a second order differential equation. Here the kx square is equal to mex over h bar square. Hence, this equation has the solution a e to the power iota kx, and a is some normalizing factor, normalizing constant. We can calculate a is equal to 1 over 2 pi under root. Similarly, for the y dimension, for the capital Y, we have this solution for the capital Z distance. If we add all these things in three coordinate x, y, z, and then x, y, z is equal to 1 over 2 pi 1 e to the power iota kx x 1 over 2 pi under root e to the power iota ky y 1 over 2 pi e to the power iota kz z, and multiply just these square roots. We have this vector, and at the end we have this type of relation. This is similar to the plane wave solution. And we can write here in terms of k and r. K is some wave vector, and r is representing the position of this particle, which is in three dimensions. These are the wave vectors x square, wave vector square, kx square is equal to this one, ky square is equal to this one, and ky this one. You can write the total energy of the system k square. It is the total wave vector along x-axis, square of along x-axis. K square is the wave function, sum of kx, ky, and kz. We are just taking the square root of k square is equal to kx square, ky square plus kz square. And finally, we have add this energy is Ex, Ey, Ez, E. This is free particle solution. H bar square, K square over 2. This is the energy of a particle who is moving in three dimensions. And it is equal to the total energy. Total energy is equal to kinetic energy. You can write here P square over 2 is 1 over half and this classical mechanics.